In today's lecture, we'll study the logic gates, the different logic gates, and how we can implement them using the MOS technology and the CMOS technology. So first of all, we'll connect two NMOS transistors in series, and we'll observe the output, whether what logic does our output follow. So these are my two MOS transistors S1 and S2. The inputs are given at the gate terminals and the output is observed here. So here I have drawn a small truth table. This is the input side for my transistor S1 and here is the input for transistor S2. When the inputs to both the transistors it is 0, what will happen? When I'm giving 0 over here and 0 over here, both the NMOS, S1 will be off because NMOS is off when a low logic level is given at its gate terminal. So S1 will be off and S2 will be off. So both the transistors, they will be off, and at my output I'll get 0 or logic level low. Fine. Then what happens if one of the transistors it is turned on? Say I'm giving 0 at S1 and at S2 I'm giving logic level 1. 0 over here and logic level 1. This will be off and S2 it will be on. But because S1 is off and it is connected in series, what will we get at our output? Again a logic level 0, or we can say at the output if we connect a bulb it will be off. Fine. Now let's give 1 and 0, that is, let me give 1 over here and 0 over here. Again the same thing will happen. S1 will be on, S2 will be off, but because S1 is on, output will be off or logic 0 because here we'll have an open circuit. Fine. Now let me give 1 as input to both the transistors. I'm giving 1 on the gate of S1 and I'm giving 1 on the gate of S2. S1 will be on, S2 will be on, and VDD it will be connected to output, and at the output I'll get logic level 1. So here if I connect a bulb at the output it will be on. So if you look at this truth table here, what do I observe? I observe that the output it follows the logic AND. When I connect two MOSFETs, two NMOS in series. So connecting two N-type MOSFETs in series will give me an AND operation at the output, and this is how we make an AND gate from the MOSFETs. Now, okay, as you know that AND gate it is a dot operation. AND is A dot B. Okay, and for dot operation we have seen that NMOS they are connected in series. Just remember these lines. Okay, these are important. Fine. Now this was when we connected two NMOS transistors in series. Let's try and see what will happen if I connect two NMOS transistors in parallel. This is simple. If you understood the previous one, you can easily understand this one. Here this is my MOSFET S1, this is another MOSFET S2, both are N-type in nature. Okay, so this is the input side of S1 and this is S2. Now when the inputs to both the transistors it is 0, S1 भी आपका 0 है, S2 भी आपका 0 है, so both the MOSFETs they will be off, and as such V out over here it will be 0. Fine. So that is what I'm showing over here. It will be off. Okay. If I connect now, if I give S1 as 0, the input to S1 as 0, and the input to S2 as 1. S1 it will be off, but S2 will be on, and VDD will be shorted to the output terminal, and Vout it will be on, or it will be logic level 1. That is what I have shown over here. Fine. Let's do the reverse. Let's give the input to S1 as 1 and the input to S2 as 0. Here S2 will be cut off, but S1 will be on, and VDD will be connected to the Vout terminal through transistor S1. So what will we get at output? We'll get a logic level 1, or it will be on. Fine. Now what will happen if I give 1 at both the gates? This will be a short, okay, and Vout again will be on. Fine. Now if you observe this logic, what will you see? You'll come to understand that when two NMOS transistors, they are connected in parallel, they function as OR gate. OR gate is on when both the inputs are on, or when either of the input is on or at logic level 1. So connecting two NMOS transistors in parallel, it will produce OR operation at the output. So OR is denoted by plus operation or the sum operation. Thus for the sum operation, the NMOS, they need to be connected in parallel. Now again you keep these lines in mind. Now this was about NMOS. हमने क्या किया? हमने NMOS को पहले series में connect किया. We saw that the output it follows the AND logic, और जब हमने उनको parallel में connect किया, the output it follows the OR logic. Now we will see what will happen when we connect the PMOS in series and the PMOS in parallel. Fine. Here I have connected two PMOS transistors, S1 and S2. They are in series, okay, and the inputs are given again at the gate terminals. So when both the inputs they are 0 0, what will happen? S1 will be on, because PMOS किस logic से on होता है? Logic level 0 से. तो S1 will be on, S2 will be on, and VDD it will be shorted to Vout, and your output it will be on, or it will be logic level 1. Now when one of the transistors, say S1, it is 0 and S2 it is 1. S1 is 0, S2 is 1 here. What will happen? S1 will be on, but here we'll have an open circuit. So Vout will be, it will be off, or it will be 0. That is what I have shown over here. Fine. Now reversing the inputs. That means S1 पे मैं क्या दे रही हूँ? 1. S2 पे मैं क्या दे रही हूँ? 0. S1 पे 1 आ रहा है and it will be off. S2 is on, but यहाँ पर क्या है? The circuit is broken over here. So Vout it will be off here. जब S1 पे 1 दिया है, S2 पे 0 दिया हुआ है, the output it is off. Now what will happen if I give both the inputs as 1 and 1? This will be off, transistor S2 will be off, and Vout will also be off over here. So if you look at this table closely, you will see that it acts as a NOR gate. What is a NOR gate? NOR gate is only on when both the inputs are low. If either of the two inputs is high, or if both the inputs they are high, then the NOR gate it shows a low value at its output. Fine. Here only when both the inputs are low, then the NOR gate it is on. Fine. For all the other cases it is off. Okay. So now NOR is the sum operation. So for sum operation, here I have written it in De Morgan's, I have used the De Morgan's formula, but NOR is basically it is OR which is inverted. So it is sum operation. So for sum operation, the PMOS, they have to be connected in series. So when two PMOS transistors, they are connected in series, जो output पे हमें मिलता है, we get a NOR gate. Fine. Now again remember these lines. Okay. Now let's talk about what happens when two PMOS transistors, they are connected in parallel. What will happen at that time? These are my two PMOS transistors which I have connected in parallel, S1 and S2, and I observe my output here. Okay. Let's check the output for different values of input. When S1 is 0 and S2 is 0, S1 is 0, S2 is 0. Both the transistors, they are on, it will be a short, and V out, it will be high or it will be on. So that is what I have written over here. Okay. Now let's say S1 is 0 and S2 is 1. S1 is 0, here 1. It is 0, this is on, this is off. But VDD, it will be shorted to V out through S1. So V out पे मुझे क्या मिलेगा? I'll get VDD through which transistor? Through transistor S1 which is on. So I'll get V out पे मुझे on मिलेगा. Fine. Now let's reverse the inputs. S1 पे मैंने 1 दिया हुआ है, S2 पे मैंने 0 दिया हुआ है. 1 on S1 and 0 on S2. S1 पे इनपुट पे जब 1 है, it will be off, but S2 it will be on. So VDD is again shorted to V out. So V out पे मुझे क्या मिल रहा है? On. But if I give both the inputs as 1, I give 1 over here and I give 1 over here. This logic. 1 on S1 and 1 on S2. Both the transistors, they will be off and will get open circuit across both the transistors. So V out, it will be off. That is what I have written over here. So if you look again at this truth table, you will understand that this is logic NAND. So what is logic NAND? NAND is that it is off for which condition? When both the inputs, they are high. That is the reverse of AND. AND आपका कब on होता है? जब both the inputs, they are high. NAND is ulta. So when both the inputs are high, it will be off. For all the other cases, it is on. So when two PMOS transistors, they are connected in parallel, I observe the NAND logic at the output. So this is how I make a NAND gate using two PMOS transistors which are connected in parallel. Now NAND is dot operation. So for dot operation PMOS, they are in parallel. Okay, remember these lines. Okay. Now this was when we implemented the circuits using simple MOS transistors. Either we used the NMOS or we used the PMOS. Now we want to implement these logic gates using CMOS logic here. Okay. Now the CMOS logic structure is as shown below. I have the pull-up network. Pull-up network is made up of my PMOS transistors, and I have a pull-down network which is made up of my NMOS transistors, and in between I observe my output. Okay, and the input, it is given to the pull-up network as well as to the pull-down network. दोबारा देखिए इस डायग्राम को. CMOS गेट बनाने के लिए अगर आपको कोई भी लॉजिक गेट CMOS लॉजिक से बनाना है, then what will you have essentially in your gate? You will have a pull-up network. Pull-up network जिसमें क्या होंगे? सिर्फ आपके PMOS, and a pull-down network जिसमें आपके क्या होंगे? NMOS, and in between we get our output. The input, it is fed both to the pull-up network as well as to the pull-down network. Okay. Now we will implement, you know that the NAND and the NOR gate, these are the universal gates. Okay. So we will implement the universal gates using CMOS. If we are able to implement the universal gates using CMOS technology, then we can implement any other gate with the help of those gates later on, because NAND and NOR gates, they are called as universal gates. Okay. So first of all, NAND. NAND क्या है आपका A dot B complement. So first of all, what you observe is that it is a dot operation. And earlier I was telling you कि जब हमारा dot operation होता है, then NMOS they are in series and PMOS they are in parallel. When I told you to remember those points at the end of every logic gate. So if you go back, let me just show you one of them here. And is dot operation, and in dot operation NMOS they are in series. Okay. Similarly, for dot operation PMOS they are in parallel. So because we are implementing a NAND gate, NAND is your dot operation. So NMOS it will be in series and PMOS it will be in parallel. So let's keep this aside now. This here is the simple truth table for NAND. The output is high when both the inputs they are 0 or either of the two inputs is 0. For these three cases the output is high, and when both the inputs they are at logic level high, the output is 0. This is the simple truth table for NAND gate. So again, keep these things in mind. Let's draw the NAND gate using CMOS. The PMOS they are in parallel. So I have drawn it with the help of two transistors. Q1 and Q2 they are your PMOS transistors and they are in parallel. And NMOS they are in series. Q3 and Q4 they are NMOS. Okay, and they are connected in series. In between here I'm observing my output, that is Y. Okay, the inputs it is given to the terminals. A हम लोग दे रहे हैं Q1 और Q3 पे, B हम देते हैं Q2 and Q4 पे. Okay, so we can say that the gate of Q1 it is shorted to gate of Q3 and gate of Q2 it is shorted to Q4. Okay, let's see whether this configuration it will work as a NAND gate or not. Okay, so what are my inputs? Inputs are A and B. The transistors, I have 4 transistors, Q1, Q2, Q3, Q4. Q1 and Q2 they are PMOS in nature. Q3 and Q4 they are NMOS in nature. And my output it is observed at terminal Y. So let me make the truth table. But before I explain the truth table, let's come to the basics of NMOS and PMOS. This is my NMOS transistor. NMOS transistor पे आपका कब NMOS on होगा? When phi is 1. Phi is the gate signal. Only when the gate signal is high, your NMOS it will be on. For the gate signal which is low, NMOS it will be off. Okay, but the reverse is true for PMOS. Here is your PMOS transistor. In PMOS, when phi is low, it is on, and when phi, that is the gate signal, is high, it is off. So PMOS and NMOS, they work complementary to each other, as you know. This was the basics of NMOS and PMOS. Now, let's come back to the truth table. Let's see whether this diagram that I have shown over here, it will implement a NAND logic at its output or not. The inputs आपके क्या हैं? A and B. Let's assume both the inputs they are 0 0 here. Okay, this is 0, this is 0, 0 and 0. A input is 0 and B input is also 0. Okay, what will happen to transistor Q1? It will be on, so I'll show it with the help of a short. But okay, and what will happen to transistor Q2? It will also be short. Okay, fine. But what will happen to Q3 and Q4? Q3 and Q4, they are NMOS in nature. They are N-type MOSFETs and they will be off because जो हमने गेट पे दिया है it is 0 and 0. So यहाँ पर आपका क्या आ जाएगा? This will be open circuit. So V out, it will be shorted to VDD through transistors Q1 and Q2. So output पे मुझे क्या मिलेगा? I'll get logic level 1. Okay, so this was the first case. Okay, let's take the second case into consideration. Okay, A is 0, B is 1. A is 0, 1, 0 and 1. So what will happen to the transistors? Q1 it will be on, but Q2 it will be an open circuit. Okay. What will happen to A? It will be an open circuit. Okay, and B it will be a closed circuit. Okay, so what will we get at the output? Output पे आपको again आपको VDD मिलेगा जो short हो जाएगा through transistor Q1, but because आपका Q3 it is open, so V out it will continue to remain at logic level 1. Okay. Let's take the third case into consideration, 1 and 0. A आपका 1 है, B आपका 0 है. A आपका 1 है, B आपका 0 है. Okay, so Q1 it will be open, but Q2 it will be short. Okay, Q3 it will be open here, but Q4 it will be again open. So V out will again be 1, that is it will be shorted to VDD. Okay, Q3 is on, but this V out it won't discharge to the ground level. Why? Because Q4 आगे क्या circuit break हो रहा है, तो it will continue to remain as 1. Okay, so this is the third case. Let's come to the fourth case, wherein both the transistors, both the inputs, that is A and B, they are given logic level 1. 1, 1, 1, 1. आपका 1 है, so this is open, this is open. So VDD it is out of the circuit because the transistors Q1 and Q2 they are open, and V out it is shorted to the ground. So V out पे आपको क्या मिलेगा? Logic level 0 here. Okay, so this is how this circuit it implements a NAND gate. If you see this output, it is same as this for the input combinations. Okay, for the same input combinations. So we were able to implement a NAND logic using this configuration, wherein we used both the PMOS as the pull-up network and the NMOS as the pull-down network. So this is how we implement a NAND circuit, a NAND logic gate using CMOS technology. Similarly, this you take as assignment. I have drawn the circuit, but you need to explain. Similarly, we can implement the NOR gate. For NOR is a sum operation. For sum operation, PMOS it is in series and NMOS it is in parallel. So you implement the gate. Here I have drawn the gate, but you have to draw the truth table and you have to write the output as well. Okay, so this is something that you can do at your own place and submit it on the Google Classroom. So this is how your NOR circuit it should look like, but I've drawn the circuit over here. Okay, now this is a very important concept. NAND versus NOR gate, which one is preferred and why? This is very important. You need to understand it very carefully. It's very simple, but it's a very important concept when it comes to differentiating between a NAND gate and a NOR gate. For example, I have to make a circuit. I can use the NAND gate and I can use the NOR gate as well for the same operation. Why? Because they are both universal gates. I can get any gate using a NAND gate, and I can obtain any gate using a NOR gate. because of them being the universal gates. So which one will I prefer? Will I prefer the NAND gate or will I prefer the NOR gate? Okay, that is something we need to understand, and that is something we are now studying. So this is the NAND gate. We have done it just now. This is the NAND gate. Okay. Suppose the channel resistance for NMOS, it is Rn, and the resistance of PMOS, it is Rp. Okay, Rn is the channel resistance for NMOS transistors, and Rp, it is the channel resistance for PMOS transistors. You know that the mobility of holes, it is less than the mobility of electrons. I've told you earlier. Why? Because the mass of electron, it is less as compared to the mass of hole. As such, electron, it is lighter and it is able to move faster as compared to the PMOS. So the resistance of PMOS, it becomes more as compared to the resistance of NMOS transistor. That is what I have written over here. The resistance of PMOS, it is 2 times, say approximately it is 2 to 3 times equal to the resistance of NMOS. For simplifying things, I have taken it equal to double the resistance of NMOS. Why is it so? Because the mobility of holes, it is less than the mobility of electron, which means that the resistance of PMOS, the channel resistance of PMOS, it is greater than the channel resistance of NMOS. Okay. I've taken it equal to 2.5 in the diagram. Please make a correction over here. Rp, it is equal to 2.5 Rn. Okay. The typical values are, it is double or triple. Okay, but here in this example, I have taken that it is equal to 2.5 times Rn. Now, okay. What is the total resistance in the pull-up network? What is your pull-up network? Pull-up network is the PMOS network. Here the PMOS, they are connected in parallel, and you know that resistance for parallel, it is connected by the inverse of the individual resistances. So the total resistance for the pull-up network or the two PMOS transistors which are connected in parallel is 1.25 times Rn. Okay, simple calculation. Okay, this is for the pull-up network. This network, it is total is 1.25 Rn. Okay. What is the total resistance for pull-down network? Here the two resistances Rn, they are connected in series, so it will simply be 2 times Rn. Now, another thing that is important to note over here is that the resistance of the pull-up network, it is called as output high drive, and the inverse of the resistance of pull-up network, it is called as the output high drive, and the inverse of the resistance, the total resistance of the pull-down network, it is called as output low drive. Okay, let me repeat it. The inverse of the total resistance of pull-up network, it is called as output high drive, and the inverse of the total resistance of pull-down network, it is called as the output low drive. Okay, so what is the total resistance of the pull-down network? It is 2 times Rn. What is the total resistance of the pull-up network? Because they are in parallel, it is 1.25 times Rn. So can I say that the resistance of the pull-up network, it is somewhat comparable to the resistance of the pull-down network? 1.25, it is not equal to, but it is somewhat comparable to 2 times Rn. Okay, what does this ensure? It ensures that the charging time and the discharging time for this configuration, it will be same. Okay, the output high drive and the output low drive, they are comparable. They are not same, but they are comparable. They are somewhat similar. So इसकी वजह से जो आपका charging time and discharging time होगा, it will be comparable to each other. It will be almost equal, not completely equal, but it will be somewhat equal. Okay, this was for NAND gate. What happens in NOR gate? Here I have drawn the NOR gate. So in NOR gate, पुल अप में P जो हैं they are connected in series and N gates they are connected in parallel. What is the total resistance for pull up network? Here pull up network में they are connected in series, so it will be simply added, that is 5 times Rn is your output high drive. Okay. What is the total resistance for the pull down network? Pull down network is connected in parallel, so it will be 0.5 times Rn. Is 5 times Rn comparable to 0.5 times Rn? No, it is not comparable. They are poles apart. So 5 times Rn and 0.5 times Rn, they are completely different from each other. They are poles apart. Okay, and as such, the charging and the discharging time for this arrangement, it will be marginally different. Okay, it will be very different as compared to what we got in NAND gate. Okay, so in order to maintain the duty cycle of the signal, in order to lessen the noise, the interference of the signal, the rise time and the fall time, in order to minimize the delay, the rise time and the fall time, they need to be comparable. And this is what we get in our NAND gate and not in our NOR gate. So it is very important to understand that both the gates, they are universal gates. Both are formed by using PMOS transistors and NMOS transistors, but they are very different when it comes to their channel resistances. The channel resistances for the pull-up network and the pull-down network in NAND gate, they are comparable as compared to the channel resistances in your NOR gate. So NAND gate is always preferred for making other gates or making the circuits rather than your NOR gate. So I hope there are no doubts in this lecture. It was very easy and very simple, but still if you have any questions, any queries, you can reach me. Thank you.